Welcome to the Rust workshop. And my name is Frederick, and these are my colleagues who we will do this workshop together for you. We will walk through some slides, and then there are also some practical assignments afterwards. Yes, some of you might have heard about Rust before. It's a funny image here. Yeah. These are some resources for you. The slides are available on GitHub. And there's also a link here to the code, which you will have to download on your machine. This is for the assignments. And we have provided some resources also for further reading, if you like the topic. This is the outline for today. I'll walk you through the fundamentals of Rust. You will probably recognize some of these things from other programming languages you might be familiar with. Then my colleague is going to talk about Rust's unique ownership model and some pattern matching, option, and so on, other concepts which you might be familiar with from other programming languages, including vectors and collections. And then if time permits, we will go also through Rust on the web and concurrency. Yes, so why Rust? Rust is a high-level language which has also which focuses on speed and memory. By this we mean that it is as fast almost as C, C++, so similar to that. But it also has some extra features, focus on safety, memory safety, so you may avoid things which might occur with languages like, for example, C or C++. It's a high-level language which allows you also to access low-level features. You can write, for example, operating systems with Rust or software on embedded devices. So it gives you access to the machine hardware. Zero-cost abstraction. By this we mean that, for example, complicated concepts like generics and so on it's compiled into quick machine code, which gives you efficiency. And Rust also has a unique concurrency model, which my colleague will talk more about later on. So it is, as you see, it's a quite popular language among developers. Okay, let's go into the fundamentals. This is probably the most famous programming example in the world. Hello World. This shows you how to declare a function, the fn keyword, parameters, data type, integer, 32 bits integer this time, and how to print a number on the screen, and how to declare a main function. You might also recognize the let keyword from other languages. And an interesting thing here is the exclamation mark. This means that this is not a function, but it's a macro. What is this? What is a macro? What's the difference between a macro and a function? A macro is, by the compiler, when you compile it, it's copied into the file compile time, so it makes it faster than calling the function. That's the idea. Data types, we have the common data types in Rust also. String, float, Boolean, Unicode characters, and integers. And as you see here, You do not have to declare the type, because Rust will infer this. So there are some default types. If you, for example, if you assign a number here, then it's automatically gets assigned to a 32 bits integer. But you can also declare explicitly the type. So here are some examples of some signed and unsigned integers. We have 8 bits, 16 bits, 32 bits, up to 128 bits, signed and unsigned integers. And there's also a special type in Rust called arctype, which gives you as many bits as your machine architecture. So on a 64-bit operating system, then you will get 64 bits, and on a 32-bit operating system, you will get 32. This is the I size or U size type. If else is like this, for example. Pretty straightforward. And types in Rust are by default immutable. You may, if you're familiar with Kotlin, for example, you have the var and val keywords, but in Rust, everything is by default immutable. So if you want to mutate a variable, then you have to explicitly declare it. There's an interesting thing here. To own, my colleague will talk more about this. This is the Rust ownership model for memory handling. So we will explain more about that later. Yeah, so I talked about immutable and mutable data types. There's a thing I got to tell you about, but there's a README file here in the in the assignments, and there are some useful. This is where you, for example, how you install the IntelliJ plugin for Rust, and how to install Rust. So take a look at that.
How's it going? Are you all done, or do you need more time? More time? I'm just going to show you about a nice cargo Rust that a cargo package that I use in my development in Rust, which is, if there are many here who doesn't use IntelliJ or Rust Rover for running the tests, like if you're just running the cargo test in a terminal, and I've implemented nothing, so it's all red for me. But I get annoyed when I have to write cargo tests after every time I make a change. So we can also install a package called cargo-watch, which I've done, so it should be fast, perfect. And then I can just run the command cargo-watch and test part 1. And the instructions are also in the README of the repo. So in this case, I can go, I got it up and running. Then I open the program in a tab. And I find the part 1. And I make a change. It runs the thing automatically. In case you don't use Rust Rover, which already had this by default. So you can find this in the README of the repo on part 6, if you feel such inclined. And now Arild is going to go through the solutions for the parts. My name is Marius, by the way. This is Arild. We're the colleagues.
Thank you. I'll walk you through the solutions. This for the part you were into just now. So first task, how to add two integers to add two integers, rather simple. Maximum of value of two integers can be done in this rather simple way too. How to check if a number is even or odd. And use modulo like in other programming languages. Yes. So this in this function you pass a reference to a string, and then you use this double quotation syntax. It's used for many things in Rust, but you can think of it like, for example, static methods in Java, for example. You call this method from. As part of my colleague will talk more about strings afterwards, and then it returns a new string which gives you ownership to that string. This my colleague will talk about in a couple of minutes. And the way to concatenate two strings, you can declare them as a tuple, and then use this two string methods on it. Yes, adding two integers we've seen before, rather simple. And how to, in the last assignment is how to access the values in tuple with the dot notation.
Third question. On line 26, you just convert S1 to a string, not S2. So what's actually happening there? You decompose into a tuple. That's okay.
Yeah.
Yes.
Yeah, the two-string part there is turning it into a complex string, and then it's this plus is then like a operator overloader, so it's calling a method. And this whole two-string and the ownership, we'll touch a lot on that in the next part. Yeah. So that's that, and then there's one more. Yeah. Okay. Yeah. So that's part one, and then I think we take a short break. We'll take a short break between each part. Grab a coffee, chat with your person next to you, and then we'll start up again in 5, 6, 7 minutes. Okay. Let's start up with part two, which is some more people coming there. Part two, which is ownership, which is Rust's memory model. And the memory model in Rust is different compared to most other programming languages. In more traditional system-level languages like C and C++, we have explicit memory allocation and explicit deallocation. While in more modern high-level languages such as Java and Kotlin, we employ a garbage collector. Rust is somewhere in the middle here. Rust doesn't have a garbage collector, but it does have a set of strict rules regarding memory management that the compiler will enforce. And it will help you with making memory access more safe and also minimize the chance of memory leaks. So let's jump straight into an example regarding ownership. So here on the first line, we create a string hello, and we assign it to S1. And on the second line, we say that the value S2 should equal S1. And then on the third line, we print S1. And that will actually give us a compilation error saying that the ownership was moved. And we have the error message at the bottom here. And at the very bottom, the compiler will say value borrowed here after move. we try to refer to a value that has had its ownership moved. So what happened was that S1 was the owner of hello to begin with, but then S2 became the owner of hello on line number 2, and then S1 doesn't own this value anymore and cannot access it. And that is the sort of the essence of ownership in Rust. And this goes for complex types like string here that lives on the heap. On the next couple of lines here, we have some integers where we do essentially the same. We say x equal 5 and y equal x, and then we try to, we print both of them. We access x. And that's okay in this example because these are non-complex types that live on the stack and they can simply be copied, and it's just a few bytes. While the hello string could be much longer, right? It's living on the heap. So then you have the ownership part. Only one owner. And well, the rules of ownership in Rust are the following. Each value in Rust has an owner, and there can only be one owner at a time, as we saw on the previous slide. And whenever an owner goes out of scope, the value will be dropped, like deallocated from the heap. And this is the essence of ownership in Rust. And let's look at another example here with how this plays with functions. So here we have a main function at the top. We start by calling gives ownership. And it gives ownership at the bottom middle here. It creates a string, guten Tag, and then it returns the string. So inside gives ownership, this sum string will have the ownership of the heap allocated guten Tag string, and then it's immediately returned. And then also the ownership goes out of this function and into S1 on the top here in the main function. So S1 becomes the owner of guten Tag. Then we create the string hello, comes into scope, and S2 is the owner of hello. And then we call another function takes and gives back, and we give S2 as an input parameter there. And takes and gives back at the very bottom, it just returns the string. So what happens here is that the ownership of S2 is moved into takes and gives back, and the ownership is immediately returned into S3, which is capturing the return value of takes and gives back. And as the comments under the main function describes, when S1 and S3 goes out of scope, then they will, well, these S1 and S3 will go out of scope, and their values will be dropped from the heap because they are owning a string value each. While S2 also, of course, goes out of scope since the main function ends, but it no longer owns anything, so there's nothing to be deallocated. And all of this happens, this all happens automatically, and if there's some sort of issue with ownership, the compiler will let you know. And also in the coding part here, you will get to deal a little bit with the compiler regarding this. And then we have a slide here on the string versus str types, because there are two string types in Rust. And the string one is the complex type, this growable heap allocated data structure, while the str is this immutable fixed length type that lives somewhere in memory, compiled into the binary, living somewhere in memory. And as the code here illustrates, on the top here we have a hello, which by itself is a str type, and then we call this toOwned, and that one turns it into a complex type. And as was mentioned in the last part, is that, well, then it's a string and it's a complex type, and then you have more methods and functions associated with it. And on the next line, we create a str. We just say borrowed string equals world, and it's a str, and also like this ampersand str, meaning that it's referring to to a string somewhere in memory. This ampersand, used in other languages to represent a reference to something. And on the third line, we create another own string, and this time that's mutable. So this let mut, then it's a mutable string. And Rust, Rust allows you to do both mutable and unmutable, as we talked about in the previous part. You can choose. Here we have a mutable string, and then we can mutate it. So another own string dot push str, and we give it the this str type, and it will add the string, mutate it.
Just one question. What was the difference between two owned and two strings?
Oh yeah, that's a good. Yeah, I actually forgot to mention it. Yeah, they essentially do the same thing. If you look at the implementation, they essentially do the same thing. I think historically it was common to use two owned, and then they have added two string, and I think that's more common today. So yeah, you can call two owned, two string. They virtually do the same thing, or you can create a string with the string : from. Yeah, I'm sure there's some small differences you want to take into account, but essentially these two essentially do the same if you look into the implementation. Yeah. And then we touched a little bit upon the reference part, is ampersand str on the code line number 2, and the rules of references in Kotlin and the coding exercises touches upon the references, is that at any given time you can have either one mutable reference or any number of immutable references. And references must always be valid. So no dangling pointers pointing to an area in memory that's not valid anymore is corrupt. And this table in the middle here summarizes the different types. We have type T, that can be owned. There's an ownership involved. If it's a mutable type, then you can mutate it, but then you cannot share it, you cannot alias it. Ampersand T means that it's a shared reference, immutable reference. So then you can share as many as you want, but you can't mutate it. And then you have the ampersand mut T, which is a mutable reference, and that you can only have one of. You can mutate it, but not share it, alias it anymore. And regarding this point number 2 here, references must always be valid. Rust has its separate concept about that. You could say that ownership is one part of the memory model, and another part is this lifetimes, which aims to prevent dangling references. But we won't touch upon that in this workshop. But that's also like a thing that Rust has with its memory model. And then I think we just jump straight into the coding exercises here. You have seen the repository. There's a part 2. For this particular one, the methods or the functions, they do have a body. So we can remove the unimplemented, and then it won't compile, and then we need to please the compiler and adhere to the borrow ship rules to make it pass. So that's the setup for this part. Okay, let's give it 10-15 minutes. Should we go through the solution or give it a few more minutes? I think we'll just go through the solution here, and you can watch if you want, or continue on the other exercises if you want to. So we have the 4 tasks coding exercises here. In the first one, I'm on master. Let's go to the solution branch here. So on the first one, we wanted to allow for mutability, and then we could mark the string as a mutable string, and then it's okay to change it, to push changes to it. On the second one, which was related to what we saw on the slides, we have simple types here that will compile and work because they don't deal with ownership. But down here we had an ownership issue because we assigned S1 to S2, and S1 would lose the ownership, and then we try to access it. So here we simply copy it, we clone it, so we get another hello on the heap, and both S1 and S2 will have its own ownership, and then it's okay to access both of them.
Is it allowed, or is there like a difference in using a reference S1 there instead? Ampersand S1.
Oh, here.
Yeah.
Oh, yeah. You can also use the reference. Yeah. That's also possible. Yeah, it's another good point.
No difference in how they behave.
Performance-wise, it's always like references because then you don't copy. And it's like in some languages, this assignment without the clone part would perhaps copy the string. But since Rust is this, this bridge between performance and more high-level languages, it was always default to the fastest option. And unless you tell it to do something, such as clone the string, it won't do any heavy computations. So it's a good point. You can also use the ampersand on the reference. And then number 3, then we get into references here, and we wanted to send the reference function instead of moving the ownership. So we had some calculate length function down here, and without the code before this was sending text into it, so the ownership was moved, and then we could not print text later on because it had lost its ownership. So as you mentioned here previously, here we just send the reference, and we can calculate the calculate length function can calculate the length, give back the length, and the ownership remains inside here, and text can still be used. And in the last one here, we wanted to call a function, append string, that would change the string, mutate the string. So here we use this mutable reference ampersand mut. So we have a mutable string here, text, and we give away a mutable reference. So the function that is called can manipulate it. And then, of course, there is a comment here regarding perhaps you shouldn't do this when it comes to mutability and mutating data at another place in code. Of course, if we work in Kotlin and Java, it's not that common to do these kind of things. You try to stay away from mutability, but in more systems level languages and really high performance, it has its place. It might be what you want to do to mutate the data in place. And that's
Can you comment on line 53 why you have to add the mute and mute and not just and?
Oh yeah, I think that's because repeat the question. Why can't we just do ampersand text here, and why do we need to do ampersand mut? That's a good question because it's already a mutable string, right? The logical thing would be that if you give it take the reference, then it would be a mutable reference, right? But I think it's just Rust being super strict about it. Yeah, that's it. So if you want a mutable reference, it's like you have to write the ampersand mut.
Maybe because it's a bad idea, and you have to.
Probably that's what the design was. Yeah.
I think append string mutate the memory, right? That's why you have to pass it as a mutable reference.
Yeah. But the question was like, why do we have to use this mut? Because you would, like, logically, if it's already mutable, you would think that it's if you pass it as a reference.
Just use ampersand, then you won't be able to push string because it's not mutable to the context of message.
Yeah. Let's go with that. Okay, that's part 2, a bit of a deep dive into the memory model. The reason why we put this as part 2 is because this is like so central in Rust, and we thought we'd just attack it immediately and then we move on. Okay, then we take a short break again before we start with part 3.
Okay, that 5-minute break turned into 10 minutes. I hope that's fine with everyone. I'm going to jump into the next part, which is about pattern matching, optional arguments and parameters, and the result, generic type. My background is a front-end developer, so I am by day as far as away from the system-level programming nonsense as compared to every backender in this room, which is why I chose to use Rust for my master's thesis, of course. And one of my favorite patterns in programming languages I explore is pattern matching, which is maybe someday coming to JavaScript, maybe, which is my day-to-day job. And optional result might also come in some subpar form, but we'll have them, so that's fine. But in Rust, I use pattern matching all the time for defining the different branches my program takes. So in this example, we have defined a traffic light enum, and enum is also a data type in Rust where you define what a thing can be. I probably used to that in other programming languages. And this main function, I define the light variable. I assign it to the traffic light enum's value yellow. And as Arild Fredrik mentioned earlier, this double colons is used many places to access the underlying value or the property. It's not the dot, which is calling the function, but we use this to get the enum value or the new function from a struct, for example. We'll get into that later. But there I'm saying that the light is a yellow light. And then I use match, which probably is very familiar for most there, match on a light value. And these 3 paths are the paths that this enum can go. So if the traffic light is red, it prints out stop. If it's yellow, it prints out caution. And if it's green, it prints out go. And I also added this line down here just to show the wildcard operator. In case you have a traffic light where you don't care about the yellow light, you just want something to happen for the red and green, you can just say wildcard, which matches on the other cases. And if you try to write this in Rust, it will yell at you because you have exhausted all the different paths. But just to show the wildcard, but if you try to write this, it will complain. And this will print out caution in the terminal. And this thing isn't just limited to enums. It's also used for pattern matching on tuples, structs, values, everything. Can really define how you want your program to flow. An option. In my world, in TypeScript, we just have a value can either be, if you want it to be optional, we just say question mark, which is shorthand for saying it can be either the value or undefined. But we don't like that in Rust. We want it to be clear and concise. So a value can, if it's an option, it can either be something or nothing, denoted by the some value and the none value. So an example, we have a main function that defines the length value. We'd say the expected type is the usize, which Fredrik mentioned is the bit size of the architecture. So it can be dynamic depending on the machine it's running on. And we call the function getLength, and we send in an option, which notice here we wrap the value with some, and then we send it to the getLength function. It expects an option of type string reference, and we want an option with new size back. And then we match on the my string, and if it's something, we just call the s.len function. This is a very arbitrary example because just doing this would do the exact same thing. But just to show the example, and then that value is either returned as some or none to the return here. And then we also get to a very common pattern in Rust, which is the builder pattern, where we just add ... on each return value. And I'll show some more examples of that later. But here we just say on the return value of this, we want to unwrap. And unwrap is one way to take out either a option or a result and just say we don't care about failing, we just want it out. So don't do that in most cases. You would have other options, but in this case, we just say unwrap if it's something, otherwise give me the value 0. In this case, we have sent in a text, hello Rust workshop, and the size is the length of it, and we get the underlying value from the option and print out length is 20. That's option. Anyone questions about pattern matching and option thus far? Yes?
Just a comment on enums.
Enums?
Something that's great with enums in Rust is that if you're matching on an enum and if you're actually not, for example, if you could have a orange traffic light and you didn't include that in your match, I mean, you do with the wildcard.
Mm-hmm.
But if you didn't have the wildcard and you only matched on red, yellow, or green, the compiler would yell at you.
Yeah.
Because there's a path that is not considered.
Yeah, so what I mentioned is also a nice thing about enums is that if you have optional values here for enum and you don't cover those cases in your match, I have in this example because the exhaustive would cover as well, but if you just say red, yellow, or green, and there's an orange light, maybe there somewhere in the world, then it would say it won't compile because you haven't covered all the cases. And Rust is very fond of being memory safe and secure, so we have to think about all options. So either you have to remove it or comment it out if you don't want to keep it. Thank you. Another question?
In this specific example, if you, instead of the underscore, could you give it none and that would still exhaust all the options?
Good question. So can we just live code a little bit? I can find out.
With the current code, if you added an orange line, then it would still compile, but in runtime it would then just go to the return message.
Do you mean none?
Yeah.
No, because none is not a type that is on the enum. And that's part of option, which is the next slide. So if it was enum had option like some red, then maybe. No. But as I mentioned, when I have the wildcard, it's complaining. You can't reach here because all other paths are reached. David?
You would need to wrap the assignment traffic card or traffic like yellow in a sun value. So light would become an option. And then you need to say some red, some yellow, some green, and you would say none.
Okay. I'm going to repeat that, but thank you for the input. But I'll just move on, if that's fine. And that's option. Any questions on option? Okay, yeah.
In Java, the option class is quite, well, you can use it as a return value, but any other use is discouraged. Because it wasn't intended that way. Is it something like that in Rust, or are you free to use it like this?
As the question is that in the world of Java, the option is something you can use, but it's not encouraged. And I've heard some podcasts talking about that issue. And what I remember is that they added it because people expected it. They don't wanted to use it, and they couldn't remove it. But in Rust, most everything is intended.
Yeah.
So it's by design.
It's fine in Java and return values,
Yeah,
of course, but not the user never possible. But it's cool.
yeah. In here it's just everything that you can do is mostly encouraged, I think, unless the compiler complains. So and result and error handling. In my world of Node and TypeScript, error handling is handled by just throwing an error somewhere in my code, and then I just hope that in my tree there's somewhere that can catch that error and print it out nicely. Otherwise, I just get an endless call stack that I have to try to decipher and paste in the ChatGPT and never find the answer. But in Rust, errors are treated like values. So when you have a result, you either pass the, in this example, we have the divide function, which takes two floating point numbers and returns a result, which is a generic type, which has two type parameters passed in. The first one is the expected value, which in this case is floating 64. And the other type is the error type. In this case, it's just a static string. And I would love to describe in detail why we have to write the fnut and static, but I haven't bothered finding out. That's just how you have to write it. That's the expected type. Anyone knows?
Lifetime.
Lifetime, okay. So you specify. Yeah, okay. It's lifetime related. So this function returns a result. And as we learned in elementary school, you can't divide anything by 0. That's impossible. So in this case, we say if b is 0, we return the value error, and then the expected type, which is a string, static string, and we send back their division by 0 error. Otherwise, we send OK, and then the value. So we can see here in these two functions that call and match on the return value of divide. We try to send in 5 divided by 0. And we match on both cases. If it's OK, we print out the result. But if the return value is an error, we print out the error instead. And we're trying to divide by 0 here. So we get this division by 0 return value. The next one, we try to divide 4 by 2, which is fine, and we print out 2. And I prefer this way of handling errors opposed to my spaghetti of catches and tries and everything in TypeScript, and probably other languages as well. So I'm just a fan of Rust, by the way, if that's not apparent. So. We have some exercises for this part as well. You find it in the part3.rs file. Any questions before we begin? Yeah?
I wonder, dina gröna finna OK och L och som och någon och sånt. Är det en slags bestämning för ord eller är det
So the question is, are these error and OK and none and some reserved words? Yes. So you can only, it's expects if you use them, you can write them in a string, but not use them as a value otherwise. You can't write and name a variable error, I think.
Yes, you can. I think it's just an enum.
Just an enum?
Yeah, I think so.
Yeah, but it's reserved.
I don't know.
Not sure?
It's in a global scope, so I guess you will get some error if you use error with capital E. But yeah. I don't think it's this scope. So I'm not sure.
That's really like one. Time's up. Was it understandable, or did you get stumped by the last parse task? I'll get you how I would solve that one in a minute. The first task, just find the value in cents. And we just match on the coin, which can be either a penny, a nickel, or a dime, or a quarter, and return the value back. Pretty straightforward. And the function get the value or 0 takes in the x as that's an option that might contain a I32 value. Then we match on it, and if it's none, we return 0. And if there is a value, we should return the value. You probably won't write this Rust code in real life, just to illustrate the examples. Subtract 1 if you want to, if the value exists and it's not 32, you just want to take 1 out. And this is the example from the slide, which is the result, where you take the numerator and denominator, and if you try to divide by 0, we get the error. Otherwise, it's okay, and the value. And for the extra bonus credit, we have one, let's just say flatten option, which just tries to move you one step into the option tree and send back the option inside the option. So just pass the option back. Yep.
Option also has a flatten function.
Yeah. Did you use that?
Yeah.
Good. There also, this is basically what you do on wrap or expect or whatever. So if you found a smarter solution or something that's from the standard library, that's better. Just to illustrate the examples from the slides. And this might be the most tricky task, where you want to take a number or input, like if you have a input to a URL and you want to extract the underlying number from the URL parameter, and it's a string, but you want to get it back as a 0 or higher. So that's when we use the unsigned number type, which is noted by U here, which is every number from 0 up to that range. But to catch that it's a negative number, you have to try to parse it as an I32, which allows for minus n plus. And this is a parse is a function that exists on most types. I input a string, it has a parse. And this thing, for those that don't know, is called a turbo fish operator, which is one way to try to guide the compiler to say what I want or expect this type to be. So in this case, I expect the parsed value to be an I32. The turbofish is something I still try to get my head around. It pops up everywhere, and I don't understand it at first, but then just try using it. You'll get there. Then I match on the value, and in this case, I used a type guard, if that's the right term for this match branch. Here I say if the converted input is either a number from minus whatever 32 bits is to plus 32 bits, or an error. Because if you try to parse something that's not a number, you'll get a not a valid number error from the parse function. There I say if to catch the negative numbers, if the converted input is below 0, return a valid error. David?
It's also worth mentioning that parse has a bound on the from string trait. So if you want to create your own parser, so to speak, then say you have a struct of some sort, if you then add an import from string, then you're able to use the turbofish operator as well with your own struct.
Yeah, so what David explained is that for turbofish, you can implement your own expected result of turbofish type operator when you try to define a struct, which we'll get in the next part. If you try to you can implement the expectant string from string, which will parse it into the expectant and try to do that, but that's more advanced, but it's possible. So here it's just done for us for the I32 and the string, but we can do some crazy shit. But here we say if the input is okay, but the value is below 0, return error. Otherwise, return the value. And then tricky bit is we have to return a U32 because we want the positive numbers. So then we typecast it to U32. Otherwise, it will yell at us. I don't have a REST analyzer on this thing.
I'm going to talk about some more common concepts that is common in other languages like Java, Kotlin, and collections and vectors. We mentioned structs just recently. As if you have been into C, for example, then struct is a concept from C. And the difference between struct and class is that a struct doesn't have any methods, like a class has a methods which is connected to the state of that object, but a struct doesn't have any method. However, as we mentioned here during the exercises, that there is actually something called an impl block, which you can add, so you can get this method too, but it's still not like classes as in Java, for example. So here we define a struct person. So it's a set of, basically a set of variables that are connected together. So this is the way to build data structures. And this is the way you initialize a struct. For example, this is the struct has a name and an age, and you access them, like an object if in Java or Kotlin with the dot notation. Vectors are collections. As we talked about earlier, in Rust you have mutable and immutable types. So also with vectors you have to define them. If you want to add elements to the collection, you have to declare it compile time. So this is one way of defining and initializing a vector. In this case, it's like 32-bit integers. We use this. This is a range from 0 to 10. We fill it with those numbers, and the collect method on the range will return a vector. Another way of doing that is by using the macro notation, as we've become familiar with a bit now. This is a vector with 3 slots with the numbers 1, 2, 3. But we can also define a mutable vector with by using the macro notation. In this case, it's just an empty or with zeros, all filled in all the slots, and then we can use the push method on the vector to add more values. So these are the resulting vectors. And of course, you can also make a vector with the struct, the person, or any other data type. How to iterate on a vector? We can use, as we've seen my colleague show you the match clause. We can use that. And the vectors have this iter method, which gives you an iterator. And it also gives you, it has a max method, will give you the maximum value. Notice the difference between these two ways of doing it. What is the difference between iter and into iter? It's about Rust's ownership model. So into iter returns ownership also. So whilst if you just use iter, you just get the reference. Closures. Yes, most modern languages today have this concept with a different name. For example, like lambda functions in Java, which is similar. It's like you define a function, So this is the syntax. So the syntax is you can do it as we saw earlier. There's a lot of implicit declaration in Rust. You can also do it explicitly. So this is the signature. It takes an integer and returns an integer, and the closure body is between the curly brackets. Another way to do it is without just by making Rust infer the type. So this will give you the same. And then we can use the closure. We can use it as a parameter to this function, our function here, which takes a function as a parameter and then execute it. So this is quite similar to other languages like Kotlin and Java. So nice, you have all this stuff from high-level languages also in Rust. Map and filter, some other stuff that you for sure might be familiar with. We have a vector here with some names of animals. And we use the into-iter, which gives us the ownership of that variable. And then we map we call the map function on the vector, and we take the length of the elements, and we filter out those which are bigger than 3, and then we'll get, and then we collect them into a new vector. So it gives us those, for example, elephant has 8. Yeah, all of them bigger than 3, since we call the filter method. Okay, that was quick, but you are probably familiar with some of these concepts from before. So now it's part 4. How many minutes? 10 minutes? 15 minutes. Okay, yeah, I think we can take a look at the solution now for these exercises. So there is a task where you have to compute the sum of the numbers from a vector of integers. You can just use iter and call the sum method. Find even numbers. Also use an iterator and then just filter by using a closure with modulo and then collect them into a new vector. Same principle, find positive numbers greater than 0. Find last number or 0 from a vector. Yeah, quick. Yes, the star is, we talked about references by using the ampersand, and the star is actually, we haven't covered this very much, but the star is actually that you dereference. So you get the value from the if it's a reference. So you extract the value. But I think filter accepts both of them. Yeah, I think. Good point. Find last number of 0 from a vector. We can use the match clause. And the last method. And if it returns, if there is none, they return 0, or else we return the reference to the number, the dereferencing of the number. Find total age from a vector of persons. We also use an iter, and then we can call the fold method, which is similar to, you might have been familiar with the reduce in Java Kotlin. It does the same. The 0 is where you start, and then you have the closure with an accumulator. and person. So then you accumulate the person age into that accumulator, and then you return. Okay, so how to find the sublist from a predicate? So we have a vector with persons, and then we can pass a predicate with, for example, get a predicate which defines age older than 18 years old, for example, in the predicate. So the predicate is a function which returns true or false. And then we use the introductory and filter, and we apply the predicate on each element in the vector, and then return a new vector by using the collect method. Find the duplicate elements in a list, in a vector. We can also use the introductory method, and then we map each element, which is here an integer, to a new vector, which is a vector which contains the same value as a copy. And then we call the flatten. Then we will end up with a vector with vectors inside, a vector of 2 elements, which has the same value. And by calling the flatten method, then we reduce it to 1 vector. Okay, and then there was a task about Fibonacci. If you remember that from high school, the Fibonacci numbers are, it's a sequence of numbers, and the next number is the sum of the 2 previous numbers. So first we declare a sequence, a vector, unsigned integers, and we call this is instance, the instance pattern, new mutable vector, and from up till the value which we supply with the parameter, we loop through that. We want to get the Fibonacci number on that slot. So the Fibonacci number, if it's 0 or 1, then you just add it to, this is the definition of the Fibonacci number, then you just add it to vector, or else it is the 2 preceding numbers, the sum of 2 preceding numbers, and we add it to the vector. So this is one implementation of the Fibonacci. There are many ways to do this also if you want to, if we talk about really big values here. And then we return the last number in the vector. Yes, then we have to dereference it too. Okay, any questions? We haven't talked so much about this referencing and dereferencing. We have talked about referencing, but not so much about dereferencing. But yeah, this is what it, yeah. Yeah, so the question is, what is this asterisk? It is, as you have the ampersand, then you, it is the reference. But when you use the asterisk, it's sort of the opposite, that you dereference, so you extract the value from it. Yeah. Hmm. Okay, so there is a break now, and then afterwards we'll talk about Rust on the web.
So Rust is a system-level programming language, which we can use high-level concepts to write and run. And as the internet knows, every C++ application is just waiting to be rewritten into Rust. That's not my saying, that's just what the internet says. But can we use this performance and security model and everything, and fearless concurrency for something more high level than on a system? And yes, we can make web servers and web pages and full stack apps with Rust. So I'll show what I mentioned my master thesis, where I'm building a web server with Rust. And I've now dubbed it Nebula, just to show what we can do with it. So here I have a full stack application which has a Rust web server in the background, which serves HTML and uses HTMX for interactivity. So this is my landing page, and the platform is a kind of function as a service that runs WebAssembly modules as functions. So here I have a test runner that tries to just. So this is why there's a Fibonacci example, because that's what I'm using in my thesis. So when I try to send in 10 to my, oh shit, there's some state from earlier. So I just spin up some, I call a function in Rust that is behind this API endpoint. And then I start up a WebAssembly runtime, which calls the WebAssembly module, runs it and sends back. And the fairless concurrency is very apparent in this setup, because I can do a very recursive Fibonacci. For those who have tried implementing that, it's a very slow endeavor. So it's just running in the background. I never figured out how long time 75 takes, but so that's a process running in the background, but I could still, oh, but I'm, no. It's a prototype. I should get that fixed. But anyways, that's just one example of what you can do with Rust and take part of the system level programming and try to make a web server, which is very performant. But for this workshop, we're going to try to implement a simple web server, which just have some endpoints where we get some text, and then we're going to use a Fibonacci thing to do the same thing I was doing on my projects. So, but what web framework should you pick? You could either write it yourself and try to figure out how to serve HTML and make your own endpoints, but I don't have time for that. So I've picked out the 3 most popular frameworks. In Java and Kotlin, we have Spring Boot, which is the standard de facto framework. In Elixir, we have Phoenix. In Node, we have Express. There are more options, but these are the most used. We don't have that in Rust yet, because it's still a relatively mature ecosystem. But 3 best options that I found is either Rocket, which I learned about when I started learning about Rust for a couple of years ago. And it's probably the most batteries included of all of them. But as I read on some posts about it, it has a bus factor of 1. And for those who don't know what the bus factor of 1 is, that's how many people who has to be run over by a bus until the project is dead. And the last, because there's just one person who does pretty much everything. And the last actual release was in July last year. So it's slow moving, but some people are still using it. And Actix is also a very good choice. Many people use it. I haven't. I use Axum for my project. So that's the one I'm using for this workshop. And Axum is built by the same people who have made Tokyo, which is what I found to be the most used asynchronous runtime in Rust to handle the concurrency. That's also a good choice. I just picked it because that's what I have experience with. Yes. So in order to, for this task, you have to get familiar with the package management in Rust. So in order to add the packages that are required, these are the ones you have to install as part of the prerequisite for Axum. And the exercises are found in part 5 in the root folder. So if you're in IntelliJ or Strover, please open that as a separate project. Unless otherwise it will yell at the analyzer can't find it. Just a hint for later. And just some basics of Axum. I have implemented most of this in the exercise. The first exercise will be just finding the typos I made by intention and try to just get the server up and running, and then add some features and endpoints. So in this example, this is the most basic one. We import some functions and structs from the Axum crate. And crate is the name of the packages in the Rust ecosystem. And we also import some the IP address and socket address structs, or I think they're structs, yeah, from the standard library.net package. And then we define a main function, which we haven't mentioned, but the main function is the main entry point for all Rust programs, like public static void main in Java. That's still a thing. And this line here, hashtag bracket Tokyo colon main end bracket, is I think it's an implementation of a trait. And what it does is it attaches some more additional stuff to the main function and allows us to make the main function async, which you won't be able to without this annotation. And then we define a app router, a new router from the Axum crate, and then we define the routes. In this case, we just have the root, which is the root level. And then we define what the get function for the root is, which in this case is a closure with where we don't care about the request or input. We just return a asynchronous hello world text back. Question?
But why would you make the main function
async? The question was why you would make the main function async. Because we want fearless concurrency, I think.
Model in Unix or Linux or whatever you're running on?
Running on Unix. Not entirely sure. This is just the way used for Tokyo. Yeah, you should read the documentation for Tokyo if you're interested. I can't answer it. I just write what the examples tell me.
I think the reason is that the Tokyo main is a macro, so that wraps that main. So that has to be async. So the actual main is not async, but I guess it's a Tokyo that is async. Okay, so I don't think the main Tokyo is async. I'm just speculating. I think so. There is some accuracy.
The source code will reveal everything if you're there. And then we use the Axum server and struct to bind a socket. In this case, we just bind it to the local host and the port 4567. And then we serve it, and we take the app router and into make service. And then we put await. And this is, as I mentioned earlier, the builder pattern. You just append a new call on each return, and then in the end, you get something out. In this case, we'll just spin up the server and wait for requests. So we're going to jump to the part 6 presentation. And after part 6, you will be able to jump into the code and do either the web exercises or the part concurrence exercises, just to have some time at the end. But I can, after part 6, I will go through the solution for the web server, and then if we have time. No break.
Yeah, let's go through part 6 too. So then you can choose if you do. Choose if you want to do the part 5 or part 6, or do both of them. Oh, nice. Okay, part 6 concurrency. Like historically, we've had two models of concurrency. Either shared memory, where you synchronize via mutexes and locks, and message passing, where it's, you don't share anything, but you communicate via messages. And it's typically implemented via channels. Rust supports both of these, but for the part 6 here, we want to use the message passing part. And the message passing in Rust, it's similar to Golang, if you are familiar with that model. So let's jump straight into our example here with message passing in Rust. So we're using this Crossbeam library, and we're calling the unbounded function from Crossbeam, and it gives us back a channel, a sender part of the channel and a receiving part of the channel. And then next we spawn a thread, which is the unit of execution in Rust. It's like operating system level threads. One thread maps to one thread in the operating system. And as we saw earlier in the workshop, we have the lambdas or the closures here, the curly brackets, which represents the body of the thread. And we also say move before the closure, which means that whatever we use inside the thread, its ownership is moved inside. You don't have to move the ownership, but here we want to move the ownership, which means that this TX, the sending part of the channel is moved into the thread. So we create the string hi and we send it on the channel, and on the outer thread we go into receive, which blocks until a message is present, and we print that. So that's the basic usage when it comes to channels and threads. And for the part 6, we're gonna look at the traveling salesperson problem, TSP. So given a list of cities and the distances between each pair of cities, what is the shortest possible route that visits each city once and return to the origin city? So there is some code in the repository for setting up all of this. So don't think about that. And this problem has the brute force approach is pretty expensive, and there are various optimizations to do. So here we have 4 cities visualized, A, B, C, and D, and the routes between them, and we can look upon it as a tree structure, and the brute force approach would be to traverse all the branches, all the paths, and find the shortest route. And I think there are many optimizations to this problem, but one is the branch and bound optimization, where if there is a early route, like A to AD has a distance of 8, and we know that the currently shortest route is 4, then we can discard that part of the tree, so we don't need to traverse that. And before we jump into the code, one more, or the code in the project, just a little bit bigger example for channels and threads, a minimal master-slave pattern with threads and channels that we can use for the traveling salesperson problem. So we start out with some work here, a vector of some numbers. Then we create a work channel and a result channel. Then we spawn 3 threads with a for loop there. And each thread is having the receiving part of the work channel. It wants to get work, and the sending part of the result channel, it wants to send the results. And here we clone the channel so that you get your own handle, and you can move the ownership into the thread that we spawn in each loop iteration here. And the thread, it goes straight into a loop, this loop shorthand notation for looping, and then we use pattern matching on receiving on the work channel. And then if we get some work, this OK number in the middle here, then we do the heavy work, number times number, and we send the result back on the result channel. And in the outer thread, we send the work on the work channel, and then we listen on all the results. and print each result. And at the very end there, we drop the sender part of the work channel. And since there is only one sender on this channel, the channel disconnects, which means all the threads will also stop. They will end up in this error in the pattern matching there, the error, and we'll just break out of the loop. So this is like a minimal master-slave pattern with channels and threads in. Let me see. Do we have? No, that's gone. Where are we? There we are. I'm just gonna take a quick show you quickly here with the code in part 6. There is this TSP.rs. Don't need to look into that. It's like the setup for the TSP problem. And here we are importing some functions from that helper file. I calculate distance and find shortest route, generate routes. There is some documentation here, but I think the simplest is to look at the sequential implementation here, which is the brute force variant with a single thread. We generate the routes given a 9 number of cities. I mean, if you have the M2 Mac, you might want to up this to 10 or 11. It's very fast. And then we have all the routes. So then we loop through all the routes. It's a vector that we looked at. And for each route, we calculate the distance, we collect it, and we find the shortest route. And down here, we have two functions that we want to implement. One would be the parallel version of the sequential one. I could use a master-slave pattern for that. And then, if you have time, try out this branch and bound optimization. Then we need some extra synchronization where you maintain, each worker maintains the currently globally shortest route, so you could quickly terminate, quickly terminate. Okay, I think that's it. Choose part 5 or part 6 or both. Yes.
Okay, we have 12 more minutes until the time is up. I'm just going to try to quickly go through the how I would solve the first task, which is to get the server up and running. I think the most people who tried it out figured out that I just had some stupid typos intentionally. So I just go through it. If you noticed in the Rust compiler, it will tell you and suggest what the actual thing is. My experience is that I am terrified of the node error messages, and I have to try to decipher. But here I get actual good advice because in web state there is no NOI value, but there is a new value. So I just try to replace with new, and it's happy. Well, not happy yet, but it's happier. And next one was this typo. It's not get, it's get. And it's not without state, it's with state. And this one is, I got questions about this one, and I can't remember, honestly, if I put this in as a actual error. But the way to solve it is to actually just define it inside the main function. And I will be happier. So this was also in the solution. Because you can't call, not sure why it won't work with constant, but I thought it did, but it didn't. And then the web server should be up and running on localhost 3000. And hello, future Rust developers. So that's the first exercise. Any questions? which is okay. And I'm not going to implement the rest of the tasks, but for the solution here, what was the tasks? Okay, the second task was to implement the get Fibonacci at nth value. So you either had to reuse the Fibonacci code you did in the previous part, or just find the Fibonacci in the solution, which is fine, and just try to get familiar with implementing a functions on a struct web state, which is the state of the application. And this might seem foreign and unfamiliar, which it is to me still. I just implemented how the mutex states to have a state that works in async. So I just implemented everything that made that work. And the focus is just to get the nth number. So you can call it in the main function and call it, send back HTML. Which looks like this. Get the nth number, parse it. And also I like this kind of way to write your code, which is the expect, which when you try to parse something that's not a new 64 in this example, you'll get this error message in your terminal or logs, so you can easier try to find the issues. So we can try to think that as writing some static tests directly in your code, instead of writing tests for this by itself. And then we get the fib from the state, which is an expose function on the struct. We print out, we then return the HTML, which is the format of the H1 with the Fibonacci number X is Y. Pretty simple. And then add that as a route here. And the next one is pretty straightforward. The same thing. Did anyone do the bonus thing with the implement display trait for web state? As David mentioned earlier, you can implement from string to influence what the turbofish operator does on your thing. You can also implement display, which is the thing that handles the formatting when you try to just write out what the state is. So the task was just to write out that the last Fibonacci number requested was this. And since you respond, you have a total of X number of Fibonacci numbers in total. And that's about it. Did everyone get this far? David did? He did yesterday? Yeah. Cool. That's part 5 solution. And I'll do part 6.
Har du den mikrofonen? Den döda. Yes, let's wrap it up with the solution for part 6 here. And if we go down here, first we have some enums here, which represents the messages that we are sending on the channels that we have for message passing. And I think you can use structs too, but enums are easy and they are nice to pattern match on. So that's one way to represent messages on, and you get like a clear naming for it, work and result. And the sequential one and the parallel one with the brute force approach is similar to what we looked at on the slides for the basic master-slave pattern. So we have the work channel, we have the result channel, and then we create the workers by spawning threads. Here we have 6 workers. And get all the workers up and running, and they simply listen for work and calculate the distance and sends back the result on the result channel. And on the outer, in the outer thread here, we start by dispatching all the work, and then we listen in on receive all the results, and drop the channel so that the threads terminates, and find the shortest route. So this is how it could look like with channels. I noticed some people used another library called Rayon, which gives you parallel iterators similar to parallel streams in Java. So that's one way to do it too. And in this case, when you have such a straightforward problem, it's probably much easier to read with a parallel iterator. But this is the message passing part of Rust. And you could also solve it with like a mutex, the shared memory approach. So many ways to solve it. And very quickly, the optimized variant down here, it's similar except from one more channel. And I think we can just go down to the worker down here, which is in a separate function. And it's similar in the sense that it still listens for work and sends back the result, but it also listens on another channel where it gets a new shortest route. So the outer thread will keep track of the currently shortest route and just broadcast it to all the workers, and they will pick it up and keep it like a local state in the thread and add it to this calculate distance optimized. So we can cut the route like the search if it's we encounter a already longer route. And here is this select macro, select guard, which allows us to like provide multiple channels, receive from multiple channels at a time, and whichever channel has some message ready will be executed. So we have that part in place. So maybe a little bit overwhelming this part, but quite fun, I hope. Any questions at the end, or? Yeah, David.
I had some floating point issues with my result ending up with 18 instead of 17.
Oh, no, I haven't. I have something to perhaps improve upon it, yeah.
Because I saw that in the property file, you were using another word for approximate.
Yeah, that's right.
Yeah, because that's here or
Okay, noted. Okay, good. Then I think we call it a day. Thank you for coming. Very nice.